One of the most popular ways to use inductive reasoning is to look for patterns. So you might have encountered this in middle school when you used input and output tables, a lot like X and Y. And so we're trying to determine expressions for terms and sequences in series. So the first step you have to do is identify the variable that is the input. And if it's in table form, it's usually the first column or the top row. But if there is no obvious value for n, for example, if I give you a list of numbers, then use the position of the number as the n. So n is 1, n is 2, n is 3. Step 2, you're going to look at how the output changes as n increases. And you're going to try a couple different operations until you're able to get the same output. So what I like to do is look at the ratio of the change in output. So when n goes up by 1, which is the easiest case to look at, how does it go up by 1 by the same amount on the output every time? If that ratio is constant, in other words, it goes up by the same amount every time, then you want to multiply that by n. If the ratio is not constant, you might try modeling the difference using n, and then multiplying that expression by n. That's a little trickier. Or even if that doesn't work, you can try a power of n, like n squared or n cubed. So those are the more complicated patterns that we'll have. Most of the time, honestly, it's going to be a linear pattern. In other words, it's going to be going up by the same amount every time. So for all of the above, even when it's a linear pattern, you may still need to add or subtract or multiply or divide by a constant to get exactly the right output. Always check your expressions by substituting in at least 3 of the inputs for n and check against the outputs. So in this example, I want to find the next 2 terms in the pattern and the expression for the nth term. I'm actually going to look for the expression first, and it helps to have a table. So here you can see I have the numbers are just listed in a row, 3, 8, 13, 18, 23. So I'm going to use the position for the input. So 3 is in position 1, so 1 for the input, 3 for the output. 2 for position 2, 8 for the output. 3 for position 3, 13 for the output. 4, position 4 is 18, position 5 is 23. All right, now I'm going to look at the change in output. Here it changed by 5. There it changed by 5. Changed by 5 again and again. That's a good sign. When it changes by the same amount, and notice that my inputs are always increasing by 1 here, then I should try multiplying this 5 by the input number. 5 times 1, 5 times 2, 5 times 3, 5 times 4, 5 times 5. Well, you can see I'm not exactly getting 3. I got 5. And instead of 8, I got 10. And instead of 13, I got 15. And instead of 18, I got 20. And instead of 23, I got 25. But I'm only off by 2 every time. So I'm going to just subtract 2 from all these. And that gives me my expression, 5n minus 2. So now I can use this to find the next 2 terms. I'm going to look for the 6th position. So I go 5 times 6 minus 2, which is 28. And the 7th position, 5 times 7 minus 2, which is going to be 35 minus 2, or 33. So the conjecture, the statement, my belief on this pattern is that each term in the pattern will increase by 5. For further reflection, here's an interesting question. We often use the ratio of the change in output to the change in input when looking for an expression. How is this ratio comparable to the slope? Well, output is the y, so you're doing change in y over change in x. Isn't that the same thing as the slope? And if I back up to my other thing, doesn't that 5 look like a slope if I said 5x minus 2? Just something to think about.